Okay, welcome back. Any questions before we get started? Okay, so we're gonna finish what we started talking about last time, and then we're gonna move on to cryptography. So these were the security principles that we talked about. We said that we start with threat modeling. That's the most important thing in any security systems. Threat modeling is about assumptions about our own device, as well as the assumptions about the attacker, and what are the key goals and objectives of the attacker. Um, it's very important to have that knowledge, and of course, you have to be somewhat pessimistic if you want to be a little bit more safe. But clearly defining the assumptions is very important. Then once we come up with the solution, we have to be very careful about the overhead and trade-offs. We should come up with a solution that is optimizing the security versus other aspects of the system, such as cost, such as overhead performance, power consumptions, and things like that. Then we talked about a bunch of different important aspects of any secure design. This includes multi-layer defense, less privilege, distributed trust, complete mediation, not security by obscurity, fail-safe device, and using isolation. So these are all principles that we usually follow. And then finally, we said that generally any good solution, security solution, should be a solution that is simple. So simplicity should be an important aspect of any design. If you can make things simpler, you should definitely do it. But why? Because complexity unfortunately causes the system to be more buggy. So the probability of having bugs significantly increase if you have a complex design. Of course, this is not always achievable, right? So it's preferred, but it's not like a requirement all the time. So what are the challenges? As we said, essentially the major problem with security is not the principles itself, but the way that we actually implement them is a critical challenge. So we usually have implementation issues and bugs in our design. This could be at the hardware design side, or it could be at the software design side. Then we also have problems called zero-day vulnerabilities or unknowns problems. So these are the problems that we don't know that they existed when we were designing the system, right? So for example, let's say that we assume that the cryptography formula or method that we are using is indeed secure. And then we build everything on top of it. For example, if you want to do some form of an authentication, we build an authentication mechanism based on our cryptography method. But let's say someone basically figure out how to attack the crypto algorithm using other types of attacks. Then essentially what happens is whatever you build, and you build it on top of these kind of basic primitive, you build a lot of software maybe on top of it and multiple layers of the software on top of it. But then if the adversary can actually break this, then it can start penetrating through the rest of the code and break your system. Similarly, there are other types of vulnerabilities, zero-day vulnerabilities in software, for example, that the adversary can kind of find these vulnerabilities and design it. This is kind of like the problem of what we call unknown unknowns, which is we don't know what we don't know when we are designing. Of course, you have to kind of expand the knowledge, and as I said, be a little bit more pessimistic when you're designing the system, but it's not always guaranteed that you know all the possibilities. Another big challenge is, as I said before, overhead. So although we want to minimize the overhead as much as we want, but sometimes it's not possible, right? So for example, you guys have seen things like two-factor authentication, which is a huge problem with many people, like a convenience problem for many people, right? But if you want to distribute the trust, that's the only way that you can do it. So there are things that you kind of have to accept when we are designing the system. Another very, very important problem, and that's actually also a huge concern, is the attack surface for most of these systems are very, very large. And unfortunately, if someone can penetrate through one of the entry points, then can compromise the whole system. That's why defense are significantly more difficult than coming up with new attacks. So for example, for those of you doing research in this area, you've seen that attack papers are easily being published versus defense papers takes a lot of effort. Mainly because the attack surface could be very large. So you can fix one problem, but then there's a whole bunch of other holes in the system that you need to kind of like also fix. But then you say that, oh no, but my focus is on this tiny thing. But then since the entire system is not secure, it's still not an acceptable solution. And then finally, sometimes we also come up with inadequate policies. And this is, again, goes back to lack of knowledge, maybe lack of investment. Many of, for example, startup companies, when they're building a product, you're so pressured about the time to market and making the product is actually functioning properly that they cannot spend much time on the security aspects of things. So sometimes they completely, neglect or don't assume the proper security system, policies for their systems, which results in the system to be obviously insecure. For example, I think one of the papers that you're going to see is looking at this pacemakers that you embody implants for helping with patients that have heart disease. During 2000, I think it was 5 or 6. At the time, Vice President of the United States was Dick Cheney, and he had a pacemaker. And there was actually a potential attack that was, by, we don't know by whom, but it was actually, they found that they can, manipulate the operation of the pacemaker. And then later on, there were some papers that shows that, for example, all the communications between the physician's kind of programmer and the pacemaker was just undeclared. So there was no cryptography, there's no authentication, there's no integrity checking and all that. Even within the device, there was a whole bunch of, some basic security principles that had never been considered. And later on, there was a whole bunch of effort in FDA and so on to regulate cybersecurity for medical devices. And now there's actually a directorate for cybersecurity for medical devices and all that. So yeah, many of the devices that has been used in the past, and none of them have been actually have a proper security. But of course, you can imagine, like, if someone attacks a pacemaker, what should be, the consequences will be. But yeah, so this, unfortunately, this inaccurate policies comes back to the cost of security, and many companies don't want to pay that cost. All right. Another thing that I want to also emphasize, and generally this is what you will see in this class, is security generally across the stack problem. We talked about this a bunch of times. And as a result, since it's kind of like an integration of a bunch of different things, and usually a security problem comes from this different integration, you can consider this as everybody's problems and nobody's problem. So many times when compromise happens, it's kind of like a finger pointing contest between different integrators of the design. The hardware says, oh, this was a vulnerability in the software. The software says this was a vulnerability in hardware. There are different components in the hardware, different components in the software, all of which could be the problem. And as a result, understanding security is generally a hard thing because you all need to understand kind of different layers. So security researchers needs to kind of have being very well versed on different topics in computer science and electrical engineering. That's generally, it's nice to kind of take courses in this because you kind of get exposed to this different areas. All right, so this is kind of like an overview of general things in security. So principle, policy, theory, cryptography, hardware, operating system, networking, programming languages, software, application, internet. They're all like, each of them has a security aspects. And in this class, we're gonna kind of, as I said, touch upon some of them. So we're gonna talk a little bit about crypto, a little bit mostly about hardware, not much about operating system, very little about network. But then we're gonna look at application and software a little bit more. So you're gonna see a kind of bits in each of them. But of course, you need to, if any of these abstraction layers is the abstraction layer that you are more interested in, you should definitely spend more time kind of like, make a deeper understanding of that particular layer. Okay? And as I said, the biggest problem in security is that they are actually controlling many critical tasks. So that's the biggest difference in importance of cybersecurity now, maybe to 30 years before. That is now, our critical infrastructures or secret data, like our banking information, our personal information, access to our homes, and all that is controlled by some form of a cyber physical system, which in the past it wasn't like that. Most things were analog and not even cyber. So that's why this is quite important. All right. So that's it from the first lecture. We can now start the second module. Any questions so far? Okay. Some few logistics. I'm going to post the reading and presentation list today, as well as the forms for review and all. The most important things that you need to do as soon as I post the reading list is submitting a Google form of your interest, of like which categories you want to present a paper in. In the form, what you will see is that there will be a box that says that do you have group members? If you have, put their names, okay? So if you already know that you want to be grouped and be presenting things together, put their names here. Only one of you needs to submit this form. Not all of you needs to submit it. So one person submit on behalf of the team, but put everybody's names in this list. Please also make sure that you're not appearing in multiple lists, okay? So figure out what is your final grouping and then submit the form that way. If you don't know anyone or you don't have enough team members, that's fine. Again, just if you don't know anyone, don't put anything here. Just put your name. If you have, for example, another person, but you want other people in your group, just put the name of the other person, and I'll kind of mix and match teams. Later next week, I'm going to post the final groupings and the final assignments. Make sure to double check that and make sure that it's correct. And the days are okay actually working for you. And then start reading the paper and prepare the presentation, okay? MSOL students, same story. There will be a form. It will be a separate form called MSOL form. So check the top of the form. I might also, for MSL students, I might actually group them in group of 2. For now, just if you have someone, if you know someone that you want to present together, you can put their name. Otherwise, I might actually group you with someone else. Okay. Questions about the logistics? Okay. All right. So this is just a reminder of the security principles. And this is also a reminder of the computer system structure. So this is what we will see a lot in this course. So essentially, the computer systems that we define in our setup, since we are mostly looking at cyber physical systems, has 5 different components. It has a sensing component, which can be any type of sensors. It could be a camera, it could be a microphone, it could be a temperature sensor. It could be any different sensors. This is generally the input to the system. Then we usually have some form of a local processing. This is the edge component of the device. So this could be any device that directly connected to the sensor. Usually this device has limited computation, limited power, and limited memory. These are edge devices, so they're mainly battery powered. That's why they have constraints on resources. Most of these devices also connect to some form of a network. This could be either a local network, a Bluetooth, for example, that is connected to a nearby device, or it could be Wi-Fi, so that it's connected to internet or larger network, or it could be even 5G, 4G, 6G, so that it's kind of a cellular network that is connected worldwide. Okay, then we have kind of the second tier computation. This is usually referred to as a cloud, which is much more powerful in terms of computation powers, usually less power less power constrained. And then I show here that this could be an edge as well. So there's actually a lot of work showing that your second tier computation does not necessarily need to be a sophisticated cloud. Could be also like a more powerful edge device as well. We're not going to get into like edge computing or cloud computing in this class, but just know that it exists. And finally, at some point, there will be some form of an actuation. Okay, so this actuation could happen directly from the local processing. So you might have these three components. So the actuation happens this way. The actuation also can happen from this point on. The actuation could also happen that this kind of like sends some data back and this one sends an actuation. So there could be many, many different combination of this system, okay? So it could be also network send some actuation, right? And actuation means any sort of physical or digital output of the system. Since mostly we are talking about cyber physical systems, the actuation itself is also physical, okay? So for example, let's say you have a car and you're driving it, autonomous driving, so you have a bunch of cameras, lidars, make decisions, and then you need to do something. You need to move the car. Another example could be like a robot that is moving around, doing different actions, and then depending on the sensors and the computations, do some actions. The actuation could be as simple as, for example, a smart lock, right? So you do authentication, you get into the app, you put in your PIN code, for example, and then lock or unlock your door, and the door being locked or unlocked could be examples of actuation, okay? Or actuation could be purely digital, right? So for example, you have a smartwatch, you press the button, something shows up on your screen. That's also considered some form of an actuation, right? So this actuation could be any sort of systems that we can consider. And as I said, not all the systems have all the components, and the computer itself is usually, we can consider it as a combination of hardware, software, and operating system. What is mostly important for us, and this is kind of like what's set this class different than other security classes or computation classes, yet we are mostly interested in interaction with the actual physical world. Okay, so our sensing and actuations are impacting the physical world. Why this is important, next time that we start talking about sensing and sensor attacks, you will see that there are a whole bunch of different attacks that sensors can be impacted by. For example, the examples that I just gave you from the medical devices, and that shows that someone can, for example, impact the way pacemaker can operate, is an example of that, right? So both the actuation is a physical actuation because it helps the heart to pump correctly, and then also the sensing is also a physical sensing. So you're going to see a lot of that. You're going to see a little bit of digital, and you will see that sometimes combination of physical and digital could be also be more powerful in terms of attacking the systems properly. So it's not just the physical world, particularly these days, since there is a lot of AI-based systems, especially for local processing. We use a lot of AI. There are a whole bunch of attacks that tries to kind of like change the sensing in order to impact the AI aspects of the things. So we're going to also to spend some time on talking about that aspects of the system. Okay? But now that we understand this, let's see how this will relate to cryptography and the rest of the system. So again, what is the thread model in our, let's see here. All right. So what is the thread model and what are the attack vector? Okay. Essentially, we can assume that any part of these systems that I show you, the sensing, the local processing, the network, the cloud, and the actuation, could be subject to attack. So in fact, we're going to actually show you a bunch of examples of different attacks at different parts of this system. So our threat model in this case is an attacker is successfully can penetrate and manipulate anything in this system. We're going to actually particularly talk about each one and then make it more specific. But generally, you can consider that this system, all parts of this system could be potentially attacked. Okay? And what is the kind of status quo of this cyber physical systems? Unfortunately, for the longest time, we didn't care about security. And the key reason is that we never design for security. As I said, most of these components are designed such that they can operate what they're supposed to. For example, if I'm designing I'm a robotic company, I care less about security at the beginning. What I do care about is that the robots can actually do its job. For example, if it needs to, pick up something and move it there, I'm not going to be worried about, oh, can the adversary kind of manipulate this? The first thing I need to figure out is that can actually my robot pick this up and put it there, right? And since this, in fact, is a non-trivial challenge, lots of engineering, lots of money needs to be thrown out. By the time that the first version of the product is out, you don't really kind of consider security as one of the factors in your system. Okay. Later on, it kind of becomes a whack-a-mole situation. Okay. So you kind of say that, oh, my robot is like, reading something from the sensor, but we never check what we are reading from the sensor. So if I manipulate the sensor, the robot, instead of moving here, can move there, right? And now what should I do? You go back and kind of try to patch things, right? So you try to patch your sensor, you try to patch your software, and so on and so forth. This actually exists in almost all the products that you're seeing in the market today, unless the product is specifically going to be designed for something that is security critical. Like, for example, if we are designing something for military applications, then sure, from the get-go, you will see that they actually consider security as one of the important aspects. But when the majority of kind of commercial use, we don't really design for security. And that's one of the key problems that we are facing with many of these systems. Okay. But this is kind of relatively changing because security has become an issue, especially since many of these companies lose millions and millions of dollars of money once their systems are compromised. First of all, there will be legal challenges because their systems cause different things. For example, if your device causing an accident and they realize that this accident is because of the negligence of the designers of not putting proper safety measures in the system, then usually there's like lawsuits by the victims and millions of dollars needs to be paid to the victims. The second thing is that usually this is like a significant damage to the reputation of the company, right? So if I drive a car and the car turns out to be easily being manipulated by an adversary, then you no longer buy that car, right? So you're worried about your safety, so you go with another brand and maybe it's more secure. If you're concerned about the aspects of data being, manipulated, misused, you're not going to use that particular service. For example, Apple, if you look at their product, you see that one of the key things that they always, advertise is, oh, we keep everything private. Your privacy is always safe. We never you look at your data, and that becomes kind of like part of their brand. Whether or not they're doing it, that's a separate story. Like what do they do with the data? But at least the branding that they have is that. If you remember, for example, a few years ago, there was this famous case for iPhones that in UK, there was this terrorist activity, and then they caught the guy and they found their phone. And in order to kind of break their phone and kind of log into their phone, they needed their passcode, right? And then, of course, they couldn't find the password, so they were talking with UK authorities, talking with Apple, that whether there's some form of a backdoor that they can provide such that they can log into the phone. And Apple didn't comply and say that, okay, their privacy of their customers, even if they're terrorists, is more important than complying with law enforcement and so on and so forth, which actually created a lot of other arguments that whether or not big companies should comply with law enforcement in scenarios like this and so on and so forth. But yeah, so there are companies like this that does this. There's another also very important, interesting case with the Amazon Blink, I think. Maybe it wasn't Blink, maybe it was some other, but one of these smart cameras companies. Maybe it wasn't Blink, so I don't want to kind of damage their reputations. Might be Ring, yeah, might be Ring, either Ring or Blink, either of these two. So what they did was they actually sold a lot of their footage to law enforcement for activities that's kind of intruders trying to get into the houses and so on. And there it turned out to be that actually this disproportionately to the Black community, and there was a whole bunch of like, also privacy violations and so on and so forth. So there are always these kind of like concerns about who access to what data and what should we do. But many of these companies, as I said, they significantly advertise their design for security and privacy as one of the key angles of their design. All right. And now the question is, okay, how are we moving toward the future? And as I said before, this is unfortunately we are like facing two important things. One is there will be much more devices around us. So if anything, we are even more reliant on digital and cyber physical systems. Not just digital, but also the way that we operate our physical world is significantly changing. As I said, things like autonomous driving, robotics, smart home applications, smart infrastructure applications, these are significantly changing our physical environments as well. And there will be like, billions and trillions of data. So, by 2020, there was about 200 billions of these devices, and this number by 2030 is going to be even more than that. Estimations are like 500 billions of devices. So what we are seeing is that it's even more difficult to secure computing devices based on this, okay? So based on these kind of assumptions, now the question is, how do we build secure systems, right? So the key idea of any of the security systems that we build in our computers comes from this very simple kind of intuition that we should start our security from something that we trust, okay? So everything else would be kind of bootstrap on top of it, okay? So in any computer system, we pick something, this could be a piece of hardware or a piece of software, and we kind of trust this, okay? Once we trust that, then we have mechanisms to kind of expand this trust to other aspects of the system. How do we do that? We use this sort of trust, which we usually call it root of trust, to kind of verify the other components in the system. So this one will verify this one, and if it passed the verification test, which I'm going to talk about what is that verification test, then you say that, okay, I also trust you. So I'm expanding my root of trust. So I'm bootstrapping trust from something small to later components in my system, okay? And again, this could be hardware to hardware, could be hardware to software, could be software to software. Could be also one device to another device. So for example, let's say that you trust your own device, you do some form of a challenge response, asking some questions from another device. If they answer it correctly and you verify it, then you start trusting that device, right? So you can kind of like do this kind of trust this way, okay? So what exactly should we trust if we are following this? So what is our algorithm? What is our approach? So we go with this kind of like assumption that we trust something that is designed correctly and hasn't been tampered with or modified. Okay, so we kind of say that, okay, let's actually gather together and think about all the possible security vulnerabilities that we're going to have. Let's design something that is robust against this, and then let's make sure that nobody can touch that, so it cannot be easily modified. Once we have that, then that would be our root of trust. All we need to do now is having some form of additional layer of like, now verifying other devices, okay? So the question is, what are the candidates? What should we trust on our computer system? Should be hardware, should be software? So this goes back to the question, this goes, opens another layer that what exactly are we really trusting in our system? One thing that we can trust is physical things that we can see and touch, right? So usually what we do trust is we trust on physical hardware that's being built. So logic and memory, they're physical entities, not the contents of memory, but the memory itself and the way that it operates, we trust. Interestingly, though, that's also not true in many cases. So there is a whole bunch of what we call supply chain security that actually questions this this very same thing that I'm saying here. But for now, let's assume that things that we build are built correctly, so we can trust them. So the logic that we put, if it's a hard logic, we can trust it. Okay. And as I said, so this is kind of like our fundamental assumption in this class. So now the question is, okay, I trust hardware. Why do I need to do anything else? Can I just do everything in hardware and call it a day? And the answer, unfortunately, is no. We need a lot of software, right? So most of you have done a lot of work in software design. Probably some of you have some exposure in hardware. Things are significantly more painful and less convenient when you're doing it in hardware. Plus, it's much more expensive. Okay, so we need abstraction layer, software abstraction layer on top of our hardware. So we need operating system, we need firmware, we need different runtime, we need software, we need software on top of software, right? If anything, we are actually shifting significantly far away from low-level hardware, right? So we are, like in the past, used to be people writing code in C. No longer that's true, right? Like people are writing code in Python. Now people are vibe coding, right? So they're even not write coding in Python. So things are even going higher and higher level as we are moving away from the hardware, so as like our trust going down and down. Because with hardware, I can trust what I build, but then everything runs on top of it, I can no longer trust, okay? So that's kind of like, the key problem. And then why can't we trust software? There are two reasons that we can't trust software. One is, the significant one is bugs, okay? So unfortunately, despite our best efforts of writing good software, there's always some form of a bug in our systems. And this number of bugs particularly increase when the systems become so complex. So for example, if I'm writing the operating system, the kernel, such as like, Linux kernel, thousands and thousands of lines of code, and unfortunately, that means that the opportunity and possibility of bugs significantly increase, okay? And the second problem that this is actually, like we're going to talk about the first one, but the second one, which is the one that we are mostly focusing in this course, is that your software starts interacting with the physical world. And physical world I cannot control, I cannot trust, right? So the adversary can manipulate things. You're going to see, for example, that the adversary can manipulate the voltage of your circuit. And if they change the voltage of the circuit, the delays changes, the way that things operate changes, and boom, even if your software is actually supposed to work correctly, since the operating condition of the system has changed, things start to be buggy and incorrect and so on and so forth. I can also literally feed incorrect data to the sensors of the device, and then that error kind of propagates through the rest of the system. So unfortunately, these are the two reasons that things doesn't go as planned, right? So we initially start with something that we trust, we verify things, but once it starts executing, unfortunately, it's not going to work. And that's why we are having lots of these different security compromises in our systems. And then what happens then? So once the adversary takes control of things, software, they can then build things on top of it. So many of these attacks are multi-stage attacks that, using some vulnerability to take control of something, then from that something, they do something else. Eventually, they take control of everything and they do their damage. So the damage could be, they can install data, they can steal data, they can manipulate data, change data, they can do some physical harm. There could be many different things, right? So depending on the attack scenario, okay? All right, but let's actually see how this process works. And let's see what we can do to make things better, right? So that's the goal of this course. Let's first of all see how do we actually even build our root of trust. And later on in the class, we're going to talk about these software vulnerabilities, and we're going to talk a little bit about, like the later half of this class would be more about, okay, how do we secure software and so on, okay? So this root of trust, or ROT, is essentially something that we assume is the smallest thing. Smallest because remember that we want to do simplicity and we want to do least privilege, right? So we make things as small as possible and use this as of root of trust, okay? And this is usually used to take us to something that we call a good known state, okay? So most of you probably are familiar with booting sequence and secure boot. So typically what happens is that when you're turning on your computer, you're essentially turning on your root of trust. Root of trust starts the secure boot process. It's verify various different things. Eventually, it verifies your operating system. And kind of boot your operating system into a good known state. That is like, okay, this is what we think that is a correct OS should look like. Okay, this is the manufacturer, new manufacturer ready kind of kernel for you to use. After that, things will be messed up because you start using it for various things. But that's at least a good point for your system. So you never start from some form of a compromised state. So when you're turning your computer on, unless you have what we call zero-day vulnerabilities, right? So we talked about 0 days. So even the good known state has zero-day vulnerabilities. These are the vulnerabilities that when we were designing this system, this kernel, this software, this hardware, we didn't know that they existed. So that's not something that we can fix with secure boot and root of trust, but everything else we can fix this way, okay? What happens afterwards? Then you're at the mercy of how good your system is and which which environment you're operating and so on and so forth, okay? So that's not the end of the story. As I said, security system is not about, oh, can we actually have a system that is fully secure and never compromisable? But rather, we need to add things that, okay, what happens if some form of a compromise happens to our system, okay? So we do also other things in order to mitigate this problem. Namely, we use isolation. So the isolation is that, okay, can I actually literally physically isolate things from each other? So for example, if I have one software here and one software here, even if this software is compromised and the adversary has full control of this software, if I have some form of a mechanism for isolation such that these two cannot talk to each other, cannot interact or impact each other, even if this software is fully compromised, this software will not be compromised, okay? So isolation is a series of techniques that we use mostly at the hardware level, such that if someone compromised part of our systems, at least the rest of the system is secure, okay? And how do we use this? So for example, let's say some security critical aspects of system. For example, let's say autonomous driving. Let's say your brake is the most important things that you need to protect. You don't want the car to be randomly braked, even if it's compromised. So I kind of wrap this part into some form of like a very secure part, isolated part that we're going to later talk about, such that even if other parts of the system, maybe your screen that shows your app is compromised and shows you random stuff. Maybe your door doesn't get locked or unlocked correctly. Maybe your car starts randomly. But again, it doesn't operate unsafely, okay? So these are kind of the techniques that we do to isolate. You had a question? Yeah, you can isolate cores or hardware from each other as well. So what you will see again later in this course, you will say, for example, the main thing that we really want to isolate is different portion of memory from each other, because memory is where bad things happen, right? So the adversary controls some part of the memory. If you can isolate things from each other, yes. But if physical attacks happens, then yeah, you can also isolate your hardware from each other. Yeah, you can isolate it from a literal physical perspective, so DIMMs from each other, for example, but you can also isolate them from the operating system level. So for example, for those of you familiar with the way that we handle address translation, you can have separate page tables, you can have separate translation, and so on and so forth. So we're going to get to this later in the course as well. Questions? Okay, so isolation is one thing, verification is second thing. So we keep checking things and making sure that they're working correctly. So, if I start by just secure boot, I only check things at the boot time. But let's say I can actually check things, once every often, right? To make sure that, things have not been changed at all. Third thing is monitoring. So monitoring is kind of like seeing whether the system is actually working correctly. Is there anything weird about the system? Is there anything concerning about the system is happening? And of course, we can always make the design better, right? So we can design for security and generally making system better. Yes? Monitoring is just looking. It's a passive thing. So you're looking at the operation of the system and see whether they're in the good state or not. Verification is an active action. So you actually check the condition and do something about it. Okay. You can verify by monitoring, yes. Mm-hmm. And usually another thing that you will see is that verification is usually deep into some form of a cryptography algorithm. So there is some form of a proof that things are happening or not happening. Monitoring is more of like, you check different things. You may be able to detect things. You may not be able to detect things. You might also have false positives. So you think that something is going on, but in fact it's not. Okay. So we said that, okay, we in hardware we trust. That would be our trusted computing base or the root of trust. What exactly do we use it? As I said, something that cannot be easily modified, easily read, or changed, okay? So what that is, this is usually referred to as TPM, or a trusted platform module. Almost every design that we have has some form of a TPM, okay? This is also sometimes called secure enclave. There's also other names. But this is basically a piece of hardware that you have on your system, such that it starts from, your trust starts from there. So when you're starting your system, this is the first thing that will boot. And everything else will be following a set of standards to kind of bootstrap the trust, okay? So you can kind of create what we call a dynamic root of trust, or DRT, okay? Which is you start the TPM, verify something else, and you start trusting that. You verify something else, you trust that, and so on and so forth. So, for example, mostly in computer systems, TPM checks the status of your other components in the system. It's to start checking things that are connected to the motherboard, and start checking the drivers of each of these things, and create some form of a hash of the drivers. If the drivers hasn't been changed and the hashes matches, you start trusting our I/O. So now I can actually receive data from the I/O. Then I go and check the status of the operating system and see whether the kernel of my operating system has not been modified or changed. If it's not, then I trust the kernel. Then I, pass the control to the kernel. Kernel starts like loading some other modules, and boom, you have the trust. You have a question? Yes. So the TPM, I don't know if I have a slide. So the question is like, are we configuring TPM purely hardware or software? So usually TPM has a hardware component, but it could also have some form of a core and some tiny program that runs on that core. But everything is inside that hardware. So what we do is that we usually TPM has some form of a logic, okay? Some small ROM, read-only memory, so that it cannot be changed. And then I can also have a core that can do some simple things, okay? So for example, all of our crypto modules that we're going to talk about is installed somewhere here. Okay. So yeah, okay, that's exactly what the slides that we have. So we have some memory to hold code and data, some functionality to verify the next step, and some basic operations. And these are typically cryptography operations. Yeah, you had a question. Yeah, you can run everything. So the question is about what exactly is the logic required for the TPM. So many things that we use as a specific, hardware designs for it. So for example, as we're going to see later, we are using encryption and decryption. Encryption and decryption is significantly faster if you have a dedicated logic for it rather than running it in some form of a software. Okay, so most of our encryption like AES, RSA, and all that are implemented in some form of what we call a crypto accelerator rather than using a core. Okay. So that's kind of like it's our bridge to why cryptography is useful. So because essentially cryptography is the pillar for trusting everything else. Okay, so we have this kind of security mechanism, hardware and software. But now in order to kind of start verifying things, we need to have some form of a verification algorithm. And that's based on cryptography functions, okay? Before jumping into the cryptography aspects of things and describing what are the key primitives in cryptography that we're going to use in this class, let me just finish this story of the secure boot. So essentially what happens is that we start some initial code stores in the TPM. That's the first step in our booting process. Then TPM start reading what is we call the unsecure memory. This is the memory that can be modified externally by the adversary. It's no longer part of the ROM. You might wonder why we don't put everything in ROM. And the answer to that is that you want to be able to interact with the memory. You want to read things and write things and change things in the memory. Otherwise, you have a non-programmable piece of hardware, which is not going to be very useful in many cases. Yes, you can have it for particular things if you don't want to have any sort of programmability, but the majority of our systems, for laptops or phones or tablets and all that, the memory needs to be both readable and writable. As a result, it's unsecure. So the TPM start reading that and start verifying piece of software stores within that memory. And that would be basically the process of establishing that trust. This is what we're gonna use cryptography for. Okay. Once we have that, then we have a new piece of code that now can be trusted. So now we add that to our root of trust, and then repeat this process until we have the full operating system fully loaded. So you usually do this in modular fashion. So smaller kernel modules. We check each one by one. We eventually have all the modules that we want to load in our system. Okay? And then, of course, within the operating systems, there are various different strategies to keep the system secure. Again, isolation, re-verification, OS verification, monitoring intrusion detections, things that we use, okay? And then, of course, if you do things at the software level, including removing buggy software or check via network and external checks, that's kind of like the things that we do. But eventually what you will see is there's an ongoing battle between the attackers and designers. Yes?
Sorry, slide when the TPM then reads unsecure memory, like where exactly is it cycling through it? You said it's not like cycling through the whole disk to see if there's any more coders. Where is it really cycling?
Yeah, so the question is where exactly the TPM is cycling through. So let's say this is your main memory, okay? And this main memory could have thousands and thousands of lines, right? So usually your operating system is stored somewhere specific in this main memory, okay? So when you're installing the operating system, you configure your system knowing that this is where your kernel is being stored. So what you're cycling through is this sequence of addresses. So your operating system will be installed in a particular sequence. You also have your device tree, so you know where your drivers are installed, where the other components of the system installed. So you know exactly the sequence of addresses that needs to be checked. Your RAM gets clear, yes, but your memory, so your disk, right? So your disk is where your data is stored, right? So your operating system is stored somewhere. So then you load that disk data to your main memory. So when you start booting, so you start loading things into the memory. That's why it's usually also very time consuming to boot your system. Mm-hmm. Yeah.
This might sound stupid, but it's like a generic. How does the OS load the disk memory into the memory if it doesn't?
Oh, so the loading is not done by the disk. It's not done by the operating system, right? So it's a functionality within the secure boot system to load things. Yeah.
So that like it'll modular check each step
and verify it. Yeah. Yes, if that's a good question. So the question is that if I'm like loading things and then start like reading these modules and some modules does not verify, what happens? That's actually what happens when your boot's kind of stuck, right? So for example, when you're installing a new driver or hardware and it's not booting properly, that's why you have this. Usually we have modes like safe boots, that what it does is that instead of checking all the modules, it checks only critical modules. And then later you can check other modules. So there are a whole bunch of like this, again, modulars within the boot systems to do that. There's also patching and hot patching that you can do. We're not going to cover it in this class, but let's say, for example, some part of this code is compromised. How do we change it? So there are these patchings that, okay, I apply some code, external code to this and replace the current code with that code. how do we do that? There is what we call hot patching, which is the system is still running and we are fixing it. There's also, you can do it statically, right? You can like literally like connect it to some form of a USB drive or some other thumb drive and rewrite the disk if you want. Any other questions? Yeah.
Is the disk boot right? Can someone modify the content of the disk so when it does the boot, it will replace?
Yeah, so this can be also rewritten if you mean an adversary, for example, rewrite the. So the question is, what if the adversary also rewrite the disk? What will happen? Yes, that could happen. And that's why we actually don't trust anything at the disk at the beginning, right? So if someone rewrite things, then what you're rewriting doesn't match with what you expect this. Because usually, again, we are using cryptography and digital signatures to make sure that no one can just randomly write. But this will goes into the denial of service kind of situation, right? So you're compromising the availability of the system, not the integrity. There could be other measures to, for example, prevent you from writing the disk. But for example, if someone has physical access, they can literally take out the disk and put something else, right? So you can do nothing about that. So you have to be, there's the there are different layers of the system. But if, for example, device is off, then you're not worried about things like network. For example, the network attack cannot happen because the device is literally off. So there are different layers. And again, it goes back to your threat model. Other questions? Perfect. Okay. And then not all the devices have operating system, right? So many devices are bare metal or have very thin layer of operating systems. They have like real-time OS. They have, some of them have some form of a firmware. Some of them have runtime. So how does those things look like? So again, there you have, instead of loading the operating system, you just load directly the applications that you want to load. Okay, so again, there could have also some measure for checking the binary of that code. Many of these very lightweight systems don't even have secure boot. Okay, so they don't check what you're loading. You could load whatever random you want, but many of them have actually some form of a secure boot as well. Instead of loading the OS, it loads the program that you want to run on them. Okay. We will talk about actually low-end devices and methods for securing them as well later in the class. If you're interested to like look into the commercial secure boot process for these different components, Intel actually has a nice, like a short white paper that explains the process. Apple actually has a bunch of different open source documents that you can read. Microsoft for Windows, they explain like how their secure boots works. So click on these links and read about them if you're interested. Okay. There's also various aspects of TCB. So for example, there is software isolation, there's more hardware isolation, there's virtual machines. We're gonna actually talk about this, I think in week 7 or week 8 of this class. So we're gonna come back to TCB more and talking about it more. Okay. All right. So that's kind of like the summary. So this is, again, so we said that essentially, do we trust always hardware? And then, as I said, the short answer is no. Later in the class, we're going to also revisit this assumption that hardware is trusted, and we show that hardware cannot be trusted all the time as well, which kind of like then destroy all of these things that we think about. But for now, let's assume that hardware is working. Okay? All right. So with that, we want to talk about crypto modules as kind of like the main primitives or systems. Any questions so far? Okay, we can have a quick break and then we can start talking about this. All right. Are we recording? I think we are recording. Okay. So the purpose of this this set of slides about crypto is not covering like a full crypto course. So there's actually there's one or multiple cryptography courses. Here we actually do have a lot of great courses: 136, 236, 282, A and B. So if you're interested in crypto, you want to properly learn crypto, you should take those courses. Okay. What we're going to do is that we're going to just touch the surface level. We're going to just give you some very basic description of things, of like what is encryption, what is decryption, what is pseudo-random functions, and what is a stream cipher and block cipher and things like that. So that hopefully you can have like some passing understanding of the crypto. Some of you, I think, already know some of these things. So it could be just a refresher. But I think for most of you, usually what I teach this class, most people don't have any background on crypto. Have any of you taken any proper crypto course in the past? Okay, 2 of you. So I'm going to ask you hard questions. But anyone else can listen. All right. So yeah, I'm not going to provide any sort of formal or proof because we don't have time, and this is not a crypto class. But there's nice books that I can refer you to, and then again, please, if you're interested in the topic, go and take a proper cryptography course. Okay. So what is the kind of the foundation of cryptography and computer security? We go with like some fundamental theoretical assumptions about cryptography. So for example, we base on some of our cryptography problems on some NP hard problems that we know exist in our systems. How many of you know what is NP hard and P hard? Hopefully most of you know, right? So generally there are, think about this again, I'm not going to go through that, but think about problems that we don't know a polynomial time. We don't know a finite answer for them in short time, okay? For example, factorization of a large prime number, it is known to be a hard problem, which means that if I give you a very, very large number, which is a prime number, it's not a prime number, and ask you to give me the prime factors of that number, it will take you a lot of time. Even if you use the most advanced supercomputer, it will take a lot of time to find the prime factors of that number. Okay? Why? Because we don't know any closed form algorithm other than just basically brute forcing through all the numbers. And if the number is large enough, for example, 64 bits or 128 bits, that means that I need to search through all the numbers from 0 all the way to the power 128. That takes a lot of time, okay? So most of these algorithms are based on those fundamental assumptions, okay? And then we make these things, as you're going to see in this lecture, based on those fundamental assumptions. So the security of our approach, which is the security of the crypto primitive, and on top of that, the security of the crypto and the entire crypto, sorry, the entire system, including our, for example, secure boot, are based on the fact that nobody can solve that critical algorithm. For example, factorization problem. And that's actually kind of quite dangerous because we are like, you probably have seen these memes that, you build a very, very kind of like, sophisticated structure and you put it on top of like a tiny, tiny thing, right? So that's kind of like, the current status. And this is your NP hard problem. In fact, most of you have heard about, for example, quantum systems and quantum computers. And why quantum computers is so a big deal is, of course, quantum can run things fast, different things fast. Particularly for security, though, quantum is very, very critical because quantum can solve the factorization problem within minutes. I mean, not the current quantum computers, but quantum computers of future once they have enough qubits, they can factorize a large number into the prime factors within few minutes. And if that works, then all of our assumptions about RSA and asymmetric cryptography that I'm going to talk about will break. And as a result, everything else, okay? That's why there's also a lot of effort on post-quantum cryptography, for example. But for now, we are not going to question the hardness of those problems. We're going to accept the fact that these are hard problems. If in future somebody can break them, then we need to come back and fix them, okay? Well, then what we do is that we build on top of those hardness problems, okay? So a high-level overview of a crypto system is a system like this, that we usually have a secret value, okay? This is what we usually refer as to a key. Depending on the algorithm and the functionality of that crypto systems, you might have pair of keys or group of keys, but typically we at least have one key, okay? Then we have some form of an algorithm. This algorithm could be an encryption, could be decryption, could be message authentication, could be hashing, could be different things. And then, of course, we have an input and an output to a crypto system, okay? The input is usually called a message, if this is an encryption, but it could be code, data, could be vectors, could be anything. And then the output is usually what we call a ciphertext, if this is an encryption, and then could be also hashing, hash of the value, and so on and so forth, okay? The very, very, very important things about a crypto system, any of them, encryption, decryption, MAC, whatever we are looking at, is the obscurity, or what we call Kirchhoff or Shannon principle, which is everything about the crypto system should be known to everyone, including the adversary, except the key, okay? So the only thing that I need to protect in my system is the secret key of the system. Of the crypto system. Everything else, inputs, outputs, what's happening within the system, all of them we should assume that the adversary knows. So security of the systems rely on the fact that I can keep my secret secure. If I don't do that, and if the key is being compromised and the adversary has access to some or all aspects of the key, then of course there's nothing remains to be secure and the system is completely collapsed. But other than that, you should not assume that the adversary does not know which algorithm you're using. As I said, in fact, all of these algorithms that we are looking at and being used commercially in all of the systems are known algorithms. Everybody knows what they are. Everybody knows how they're being implemented and so on and so forth. Okay? So there's difference between different definitions in cryptography. We have what we call usually cryptography primitives, okay? The other names also being used in different resources, but these are kind of like your main basic blocks. So encryption, decryption for symmetric, asymmetric, secure hash function, message authentication code, and digital signatures. These are the main primitives that we use in our cryptography. In fact, these are the things that we're gonna actually go over in this lecture, okay? Based on these primitives, then we build protocols. So for example, someone asked last time, what is zero knowledge proof? Key exchange. Probably most of you have heard about TLS. So smart contract, blockchains, secret sharing, multi-party computation, authentication, logging, all of them are some cryptography protocols. These protocols are built based on the primitives, okay? So they're built based on encryption, decryption, message authentication, hashing. So if you, for example, spend some time, some of you, I think, knows what is, how many of you know what is a TLS? Okay, few of you. So that's okay if you don't, but like if you have taken the course in networking and all, you've probably seen this. This is actually a layer built on top of these primitives that tells you how do you communicate on the internet, for example. How do you send a packet? How do you receive the packet? How do you know this packet is actually being sent by this IP address, and so on and so forth. So these are all based on this simple primitives. We're not going to talk about the protocols in this class at all. This is all, again, when you're looking at these primitives on other classes, but we're going to talk about these primitives, okay? All right, so let's just start with the encryption, decryption. This is the most intuitive one. It's the one that you have seen, and you know exactly why it's being used. Because when I want to communicate between two parties, I want only these two parties understanding what message is being communicated. Everybody else that sits in between and see the communication will learn nothing about the system, okay? So more formally, this is a crypto system that does encryption and decryption. So for encryption, we have a function E, okay, that takes M and K. M is your message and key is your key, secret key. For now, let's assume that we only have one key, and we're going to talk about what we call symmetric encryption. And the output of this system is what we call a ciphertext. It's a C, okay? Decryption is the opposite of this problem. So decryption is an algorithm called D. That takes, again, this time the ciphertext and again key, same key, and gives you a message, okay? Important property of any encryption system is correctness, which means that if I decrypt an encrypted message, I should get the message. If I don't get my message, then the entire purpose of encryption and decryption is meaningless, because I send, for example, yes, I decrypt no, that's defeat the purpose, okay? So anything that we build has to have this important property, which is the correctness property. Then depending on the crypto systems, there's a whole bunch of other properties. For example, there is one property that's being used a lot, which is called homomorphism, okay? So homomorphism basically says that if I have a function that applies to my plain text, so M1 and M2, if I apply to the encrypted version of the message and then decrypt it, I get the same message. So for example, let's say, so let's define this F as just a simple addition, okay? So what does homomorphism tell you is that if I have one message, let's say my message is number 3, let's say I have another message and this message is number 7. What this tells you is that if I apply add to 3 and 7, I'm going to get 3 plus 7, okay? So I'm going to get 10. What this one says is that if I have some form of an encryption mechanism, so for example, I encrypt M1 and I get some encryption message. So maybe 3 will become 17, okay? So it's just some form of an encryption. It could be any function that is applied, okay? And then if I encrypt 7, I get maybe like 53. I don't know. Again, I'm just making up numbers. Then what this says is that if I add these two together, so 17 plus 53, I get 70, right? And then I decrypt this 70. If this homomorphism applied, I should get back 10. So for example, let's say my decryption is, I always divide this by 7. Some random decryption, okay? This is kind of like the property that we are interested when we want to apply some functionality to my encryption. But majority of encryption systems that we learn doesn't have homomorphism. And this is just homomorphism over addition. You can have homomorphism over multiplication. You can homomorphism also over other functionalities. But for now, we don't care about this. What we do really care about is decryption and encryption. So we want to have a correctness property of an encryption system. So before I actually show you how do we do this, let's actually ask you, what do you think a secure encryption algorithm should look like? Like, what do you call something secure and what do you call something insecure? Yeah.
If you have just like only the
Mm-hmm. Uh-huh.
you shouldn't be able.
Yeah, so if I see the ciphertext, you should learn not much about the message. Okay, can you now be more specific about what sort of attacks you think you can do? So let's say, for example, I have yes and no as my inputs, okay? And I encrypt yes and I have some ciphertext, so maybe like some gibberish. And I also encrypt no and I get some other gibberish, okay? So if I see these two gibberish, the first question, of course, is I should learn nothing about the message. For example, maybe the sizes of these ciphertexts should not be correlated with the sizes of the message that I have. Okay, so maybe they should be the same size. But what else? Yeah. Uh-huh. Yes. Mm-hmm. Yes, exactly. So what the answer was is that not only I have to not like looking at the separate C's, I should not learn anything about M. I should also not learn anything about the distribution, right? So if I see many ciphertexts, they all should look different so that I cannot say that, oh, okay, 9 of them look similar, one of them only looks different. So maybe this one is no, because I know the probability of no is less than yes, okay? So the distribution should not be also revealing any information about your system, okay? So nothing about length, nothing about distribution. What else?
So you said we nine yeses so we also factor in some some key that's individually specific to each person who respond.
So are you asking like how do we actually do that?
How do we like we know that we just made it. We put the function on yes, put the function on no. Then we're obviously just going to have one gibberish that's exactly the same.
Yes.
Either no, another.
Yes. So that's a great observation. So encryption function, if it's deterministic function, you're going to always get the same answer. So that's actually the answer to their question. So how can we get a different gibberish for every time that I'm encrypting a yes? Then your encryption function should be what we call a probabilistic function. So it should actually generate different answers each time you ask it. And then we're going to get to it. So don't go farther than that, because then you will ask that, okay, how do we decrypt if it's probabilistics? There are solutions for it. But good observation. Anything else? Think about from the attacker's perspective. Yes. You need some mechanism for knowing that the ciphertext hasn't been tampered with. So is it originally coming from the message that that's actually a great point, and that's true. That still goes to the integrity of the message, not the confidentiality part. So there's actually, later you're going to see that we have what we call authenticated encryption, which provides both integrity and confidentiality. For now, let's say that we're not worried about that part yet, but we're going to see that later. You're about to say something, or?
I'm just gonna be like possible force. And then just like try and keep bashing until you get the right.
Yeah. You can brute force, so you should be resilient against brute forcing, right? Which goes back to like I should learn nothing when I see C. This should give me no information whatsoever about M. Okay? Yeah. So this is actually this is true. In fact, actually, what we can do in addition to brute force, which is more sophisticated attack, is what we call frequency analysis. Okay. So imagine that I have some form of a one-to-one mapping between every character in English to the crypto systems that I have. So, for example, A becomes B, B becomes C, C becomes D, or could be any random mapping. Okay. If my encryption system is like that, then what will happen is that attackers can do what we call a frequency analysis. I know, for example, the distribution of different characters in English words. So I know that, for example, A and D and E and A are actually the most commonly used, and also T are the most commonly characters used in English words. Okay. So what I can do is that, although I don't know the exact mapping, what I can do is, if I see the encrypted message, I do a frequency analysis on the encrypted message. And I see the character that's been repeated the most of the time, it's most likely E, right? Or the second choice would be A. So I still do brute forcing, but an informed brute forcing, okay? Some of you, have you guys watched this movie called Imitation Games? Okay, one of you watched, two of you. Are you guys familiar with this guy named Alan Turing? Right. So Alan Turing is also called as kind of the founder of the computer science. He come up with this machine that breaks this cryptography engine called Enigma machine. Okay. So Enigma machine was. Do I have a picture of it? I don't. So I'm gonna post some. So Enigma machine was this machine that was used by Germany during World War II to encrypt their messages. Okay, so it was like a typewriter. Okay, so it was a typewriter, but then there was internal mapping of the typewriter that map each character to another character. Okay, so if, for example, a German officer wants to type something, they just use the regular typewriter. But as it was typing, it was mapped internally with some other other mapping. So the message was just generally like some other weird mapping of the sentence. Okay, and all they need to know from the receiver and the transmitter was knowing this mapping. Okay, so if they know the mapping, both the receiver and transmitter, they set up their typewriter such that these two mapping are the same. So when I actually type that back, I will get the original message. And this was how World War II Germans and Nazis were using this method for communicating. Okay, And in order to fix this kind of frequency analysis, what they did was kind of like they keep changing their mapping such that it's not easy for the allies to figure that out, what exactly the mapping, okay? And they kind of do some analysis, and every day kind of they change the mapping. But the interesting thing, though, was there was a sophisticated thing that Turing found and their team found, was that they start all of their messages with the exact same word. They started with saying "Sieg Heil" each time that they were sending a message. And they used that over time to actually do the frequency analysis, and they found it, okay? But there's actually lots of interesting stories about Enigma machine. And if you watch this imitation games, there's also, you can see the story behind it. But overall, there are a whole bunch of differential analysis attacks, frequency analysis attacks, brute force attacks, depth attacks that exist in systems. So your crypto system should be basically secure against these type of attacks. Yes, sir.
Wait, didn't they also like figure out? So like every time they encoded a letter, they never used the same letter to encode it. So like if you encode A, like it would never show up as.
Yeah, well, yes. So instead of searching for 26 characters, you always search for 25 characters. But it's still, the mapping is so large that it takes a while for you to do the brute force.
Well, like, I mean, wouldn't, but I thought that was an exploit, because by knowing that, like, you will never use the same letter to decode.
Yes.
You can kind of like,
yeah, you can reduce the search space, right? So, but it doesn't completely solve the problem. But yeah, that is true. That if you never, like, you never map it to the same character, so you have less of a search when you're knowing. Yeah. In fact, you can actually, I think there is this website called Enigma Device or something, that it's like Wordle, that each day there is a sentence. You can actually try to do frequency analysis and fix it, find it. And change every day, like a Wordle puzzle. If you're interested, you can search that too. All right. So now that we understand this, let's actually talk about what should be a secure encryption algorithm look like. Okay. So a formal definition of the encryption algorithm should be that it should be hard to completely determine M from C without the knowledge of K. Okay. So that's the definition of a secure encryption algorithm. Okay. So when I say determine, then you might wonder, does partial understanding of the message also consider secure or not? Okay. Or should I like completely understand M? So for example, if N is 5 characters, if I know, for example, what is the first character, does that consider secure or not? Right? Second question is, what are the attacker's capability? Does the attacker only sees the ciphertext? Or does the attacker also knows what is the plaintext? So it sees the plaintext and the ciphertext and tries to find out what was the key. Or does the attacker also can choose the plaintext? So for example, the attackers can say that, okay, this is your crypto algorithm. I pick these messages and I want to see what is the ciphertext for each one. And I want to find what is the key for this encryption algorithm, okay? So these are different capabilities that we have, okay? Typically what we want to do is that at the very least your attacks, your crypto system should be secure against what we call a CPA secure, chosen plaintext attack secure. That is, if the adversary can choose their own plaintext, they still should not be able to figure out what was your key, okay? So it knows everything about your system. Input, output, algorithm, does not know the key, should not be able to tell what was your key that you used for this, okay? And then the second problem that we need to figure out is, as I said, it should be completely hard to determine M from C without knowledge of key. But as we talked about is, if I encrypt yes 2 times, I'll get the same C. So if I know the distribution of yes and no's, then even though I see C and I don't understand what is M, but distribution of C should not also tell me anything about the message itself, okay? So in order to fix that, we kind of add this part to our original definition. So let's say we are seeing 2 messages and we are seeing C, okay, for each of these messages. Based on that, there should be equal chance that C belongs either to M1 to M2. In other words, the adversary capability of distinguishing whether this C belongs to M1 or M2 should be exactly same. It should be 50%. So it should be random guessing, okay? So with that, this is what we call perfect secrecy, okay? So perfect secrecy, which is kind of the gold standard in encryption, is the following, that for all M0s and M1, all M0s and M1s in M, so if I have a message space, let's say all the words in English language, and all C's in C, so all the ciphertext that I can generate in the ciphertext domain. So let's say, for example, I take any word in English and I create an encryption ciphertext that is 64-bit long, okay? So all the numbers from 0 all the way to the power of 63 minus 1, and some random variable k, which is your secret, then it should be that is uniformly distributed over k. So this k could be any number from the key space. Then we say something is perfectly secret if the probability of encryption of message 0 with key k equal to C is the same as the probability of message 1 being encrypted with key k and being equal to C. In other words, what I have here is the following. So let me give you an intuition. So let's say these are all my messages in the M space, okay? And let's say this is all my C's in the C space, okay? So if encryption is some form of a function that maps a message to a key space, this probability that this is mapped to this should be exactly same as this one maps to this, as this one maps to this, and so on and so forth, okay? That's what we want to achieve in a perfectly secret. And the same way for all the different C's. So probability of things that map in this one should be equally distributed between all the M's. You have a question? So key is a sample space, right? So let's say key is all the numbers in 32, like let's say the size of your key is 32 bits. So any number that I can just randomly sample from that key space, any number between 0 to the power of 31 minus 1, I can use as my key. So I'm saying that I can choose any of the numbers in that space and use it for this encryption mechanism. I still don't talk about what is my encryption mechanism. But if I apply that k and M0, I should get C. And the probability I get C should not be dependent on the message. So any message that I use, same probability I'm going to get C.
So what's this? Like the hacker should not guess your key by something like not.
Yeah, so this is more of like what is the right way of generating the key. So key should be uniformly distributed against k. So it should not be, for example, what this says is that there shouldn't be some keys that doesn't follow this. It should be all of the keys that we are seeing in this space should follow this format. Another question? Okay. Any other questions? Good. All right. So how do we achieve perfect secrecy? Is there any actually function? There's any E function that can achieve this? And surprisingly, there's actually very, very simple function that achieves this capability. And that's called one-time pad or OTP, which is basically all it does is XORing K to M, okay? So if I take a message and sample a key and I XOR it and I get C, that would be satisfying my perfect secrecy, okay? The only tiny requirement is that the size of the message and the size of the key has to be the same, okay? Because I want to, this is a bitwise XOR, okay? So I need to have a key as the size of the message. If I XOR it bitwise, I get a ciphertext also the size of the message, but this will satisfy perfect secrecy. Why? There is a very long proof for it, but you have to take my word for it that XOR is good enough. It gives you perfect secrecy. Okay? Say again. You can, yeah. There is a long proof for it that is actually showing that this gives you a uniform distribution. The nice thing about XOR is actually it follows the distribution of the key. That's why this is secure. Okay. So essentially, the encryption is the following: that I take message, I XOR it with the key, I get my my ciphertext. For decryption, I take my ciphertext, I XOR it with the key, I get my message. The reason for this is that XOR has a dual property. So XOR of something with so this will be basically similar to this, right? So C would be itself would be M XOR K, and then this would be XOR K. And then what you can do is that you can write this as like this. K XOR K. Something XOR with itself is 0. Okay. And something XOR with 0 is itself. That's why you get that. Okay. So one-time path, very simple. Key has to be size of the message. And you will achieve perfect secrecy based on this, as long as your key is uniformly distributed in some domain K, and your message is also uniformly distributed in some domain M. Okay, questions? Okay, so what is the problem with OTP? Anyone wants to comment? Yeah. You can use it more than once, because if I keep XORing the message with the same key, I will get the same C. So that's the first problem that I'm going to have, right? So one-time path is not probabilistic encryption, so it doesn't solve the second problem that we have. If I keep encrypting yes, I keep getting the same C, right? What is the other problem with OTP? Yeah, messages. Well, messages can be arbitrary length, but then your keys should be the same size. So imagine that I want to encrypt 1 terabyte of data. I need another 1 terabyte of key, right? And storing key is difficult because I need to keep it secret. Transferring keys is also very difficult because remember, for decryption also I need to have access to the same key. So I need to somehow move the keys to the receiver, and that also creates a bunch of problems, okay? So problem number one is key and message should be the same size, and this is a practical issue. It's not a security issue, it's a practical issue because I essentially need 2x storage for storing 1x message, right? So for 1 terabyte of data, I need 2 terabytes of storage, right? And even worse is that I need to kind of transfer the keys all the time. The second problem is many-time path or two-time path is not secure in this algorithm, right? So if I do OTP for yes and no with key K, if I do it twice, I get the same answer, and that's not what I want, right? So I don't want my encryption to be deterministic. I need what we call a probabilistic solution, okay? So how do we fix this? We're going to talk about the first one first, and then we're going to later come back and fix this problem, okay? So what we do, and this is actually a breakthrough in cryptography space and research, was we relaxed perfect secrecy and we changed it to what we call semantic security, okay? So what is semantic security? Semantic security is saying that, remember I told you that the probability of EK M0 and EK M1 should be exactly same. So probability of this minus this has to be 0. Semantic security says that, okay, let's not make this 0, but let's make the probability very, very, very small. So we say that this is not exactly 0, but it should be negligible that the probability of this message and this message should be the same, okay? If I do that, then there are lots of interesting things will happen. Particularly what will happen is that I can have much smaller key size that I can use to stretch and use it to do one-time path, okay? So you might wonder, okay, how much is negligible? So what should be that epsilon? Is it 1%? Is it 10%? Is it 0.0001%? What is negligible? And this is basically a parameter or a factor that is designed in the crypto system. So it's not like a one single answer, but rather it depends on the level of security. So crypto systems also become some form of a trade-off between security and overhead and other aspects of the system. So this is the parameters that we choose. Typically, we choose some very, very small number. So for example, we choose something like 2 to the power of 128, okay? 1 over 2 to the power of 128, or 1 to the power of 256 or 512, depending on the crypto systems and the security requirement. But this is a very, very small number. So when I say negligible, we are talking about very, very, very small numbers, okay? So what is the major use case of semantic security? Again, there is a proof. I'm not going to talk about it, but what semantic security tells you is that with a proper stretching algorithms that I'm going to talk about soon, I can use OTP with a key that is much, much smaller than M. Okay? And then I can basically, what I do is that I take K, I feed it to some stretching algorithm, make it size M, and then apply OTP to it. Okay? So basically what this says is the following, that remember I told you that essentially C is equal to M XOR with K, and I said that the size of M should be equal to the size of K. Now with semantic security, and assuming that I don't want perfect secrecy, but I'm okay with a negligible probability difference, what I can do is the following. I do C M XOR with some F of K, okay? And what is this F of K? I call this a stretching algorithm. We're going to talk about it later with what we call stream ciphers. But this F of K is basically this, that it takes a K that is significantly smaller than M. So let's say you call it K1. You feed it to this F, and it gives you a K that is same size as of M. Okay? Just think about it as the following. Maybe like the most stupid thing I can do is that I repeat K1 multiple times. Okay? It's not going to be secure, and that's not what we do. But let's say, for example, K1 is only 8 bits, and I want a secret key that is 128 bits. So I repeat this multiple times such that I achieve the 128 bits. I take that, and I apply my OTP, and this will be my encryption code. Okay? Now, of course, the question is, what should be this F of K? It cannot be any arbitrary algorithm. It should be some algorithms that is somewhat secure, as we're going to define later in the class. Okay? Any questions so far? Before jumping into that, there's also another thing called message recovery attack that you can also think about it as somewhat similar to semantic security, although it's a slightly weaker model, which basically what message recovery says is that if some challenger encrypts a message M prime in M and send it to you, then the chance that the attacker can correctly guess the message, that whether this is M or M prime, should be 1 over M. In other words, if I have a large message space, okay, I should not be able to tell the difference between which message is being encrypted by more than 1 over M plus some tiny epsilon. So if I have many, many messages, if my message space is large and then my epsilon is very, very small, it means that I cannot distinguish between the messages that's being encrypted. Yes? Who should know the stretching function is the transmitter and the receiver, both of them. Mm-hmm. Another thing that comes from semantic security, yes. No, so actually a stretching function is also known to everyone. The only thing that is kept secret is K1, like your seed. Yeah, for example, you can do SHA, but SHA is like from higher space to lower space. You need something that's stretch. Yeah. So there's like cha-cha, salsa. There's like these algorithms that actually does that. AES also has its own key expansion. Any other questions? Okay. So another thing that semantic security gives you is that not only it tells you that you cannot tell individual messages from each other's, you can also not tell individual bits from each other. There's actually a very nice proof for this that shows you that guessing individual bits of a message should be also random. So it's not like, if one bit is more likely to be 1 versus 0, this is not going to give you semantic security. So if I have a message or of a length L, each individual bit is basically random guessing. Okay? Just keep that in mind because this is very, very important. Essentially, this means that the adversary cannot say that, okay, I know the first 2 bits, and then the rest of it I'm going to do brute forcing, because then this essentially reduce the length of the brute forcing. Semantic security guarantees that every single bit in my message will be randomly guessed. So there's an equal distribution for every single bit, not just the message, but the entire bits. Okay? So how do we build this semantically secure? Let me very quickly talk about this, and we're going to come back to it next time and talk more about this. So this is what we usually refer to as stream ciphers. Okay? So the idea is the following, that we start with some seed, okay? That is your K1, that is your smaller secret value. Then we use a stretching algorithm that expand this into the size that you want, okay? Under certain condition for the seed and the stretching algorithm, this will give you semantic security, okay? So more formally, this is the definition, okay? So if I have some S, okay, this is your seed, that is bits, okay, and bits of length L. So let's say, for example, L is 8. So I have seeds that are 8 bits, okay? And I have my message and ciphertext also bits a size capital L. And of course, little l is much, much smaller than the capital L, okay? So for example, let's say your big L is 128, your little l is 8 bits, okay? Then your encryption and decryption under the stream cipher looks like the following. So it takes S and M. It does do G of S. This is the generator function. And XOR it with M. Okay? Decryption, same story. Takes D, S, C. G of S gives you the same secret key. You XOR it with C. You get your message back. Okay? The big thing about G of S is that G of S should be random looking a string of R. That is, for the adversary, it should be difficult to distinguish the sequence coming out of G of S than any random looking sequence of the size L. So if I have, let's say, L is 128 bits, I just pick a random value from this space, okay? So I pick random bits, zeros, ones for every single bit, and that is my R. G of S should look similar to that in terms of randomness. Of course, not exactly. With semantic security, it should be the probability of distinguishing between G of S and R should be less than epsilon, okay? So if my generator function takes the seed and creates some random looking sequence of bits, that random sequence of bits should be looking similar to a true random sequence. When I say truly similar, how do I know that? There's a whole bunch of standard statistical tests that you run on G of S and R, and these random statistical tests should be passed when I say G of S is a secure stream cipher. So for example, I check out the distribution of individual bits. There are a whole bunch of other tests. There are actually the National Institute of Standard has this sequence of standard tests that you run, and you get your answers of whether this is random or not. Yes? G of S as in constraint, you mean like the size or constraint? Yeah, so g of s is a deterministic function. So you know exactly what it does. Yes. So you actually, as a cryptography designers, you design this g of s. So as I said, like there are known algorithms like RC4, Cha-Cha, you know, these are actually g of s's. Yeah. C?
The seed.
Oh yes, the seed is your secret. Yes. Uh-huh.
I keep like a separate G and a separate S.
So S is your secret key in this case, okay? So S is what is the secret value in this crypto systems that is known by the transmitter and the receiver. G of S is a known function. So everybody knows what G of S is. They don't know what S is, but they know what G is.
What's the point of having an S in S?
Well, then how do you generate key, right? If I don't have S, how do I generate G of S?
Why not just always have G of S and keep that around? Like both sides just store G of S.
Oh yeah, so both sides, like why do you want to store G of S instead of the results of G of S? That's what your question? Because it's significantly more beneficial to store S. S is very small number, right? So for example, S is only 1 byte. I'm storing 1 byte. I have a function that can stretch it to a long number, right? Instead of like storing the big key. And also remember that we keep generating these keys. So usually we have what we call session keys, for example, for these protocols. We don't ever just use for the entirety of like lifetime of an application, just use one key. We keep changing the key depending on the sessions. So it's not beneficial to store a lot of keys, but rather the smaller seeds and then generate it. Okay? Yeah. We're still vulnerable to many time path. Yes, this does not fix the problem of many time. All right. Thank you, guys. I'll see you next time.